Okay, to finish off our trilogy with phase changes, we're going to look at a more comprehensive view of how to determine the amount of heat either absorbed or given off when you're doing phase changes that involves more than one change. Previously, we dealt only with the change within the phase and going out of the phase, but not dealing with the aftermath. We're just taking a one-sided view of that. This time we're taking a 2 or 3 change process and taking a lot of things into account for that. Now, let's start with the first example to talk about how this is going to work. We want to know how much heat is needed to melt a 45-gram chunk of ice when the temperature rises from 0 to 25 degrees. Remember, ice is going to be ice at 0 degrees Celsius. It can be colder, but we're going to take it at the point where it's starting to melt. And so we have to do 2 things when this occurs. The 2 things we have to do is melt the ice, and that's going to be a phase change. We're going to change the ice into liquid water. Now, in order for that to take place, we are not going to change the temperature of the water. The water is going to stay the same as the ice, which is 0 degrees Celsius. Then it's going to get heated up after that to that. Now, not all of it's going to melt at once, but once it starts melting, then the heat change starts to take place for that temperature change. At the post-ice phase. In other words, now it's going to be completely liquid. So there's the ice phase here, then there's the post-ice or liquid phase here. Now, it's going to involve 2 different equations. The amount of heat here is going to be the mass. When I say mass, it can be either grams or moles, depending upon what is going on with our value here. In this case, it's kilograms, so it's going to be in grams, or actually kilograms. Let's make that a kilogram right there, times what we call the latent heat of fusion, the amount of actual heat it's going to take for it to go through this complete phase change. So that's L fusion, or L sub F, which is often used. I put the FUS to emphasize the fact that it's not freezing, because that would be a negative value instead of a positive value. This is going to be totally endothermic. The second part of this process is going to be the temperature change. And now we have to take into account the T value, how much the temperature change is going to have an effect. Now, the latent heat of fusion is supposing just no change in the H2O solid at that point. But once it becomes liquid, now we're dealing to a new phase, which involves the mass again, times C, which is the heat capacity, which I'll talk about in just a little bit, times the change in temperature. So we'll call this H1, and we'll call this H2, and we're going to add those 2 together. So the total heat is going to equal to H1 plus H2. So we have to do these in these 2 stages here. So, first thing we need to do, let's take the ice phase, and we said the heat is equal to the mass, which we identify here as being 45 grams. But the issue here is the fact that we have a value for our L fusion in joules per kilogram. So we're going to have to change those grams into kilograms. We'll do that right away. 1 kilogram on top and 1,000 grams on bottom. So the grams cancel out, and that's going to be our mass. This is our mass right there. Times our L fusion. And the L fusion we said here is 3.33 times 10 to the 5th joules per kilogram. Okay, so this is our H1. So if we go ahead and work this out according to my calculator for that, it's going to give me H1 is going to be equal to 4710 joules. Now I've been known to make mistakes. If you don't feel this is correct, let me know, and then I can make the appropriate changes on the Google Classroom site. But this is what I got for that. So that's H1. H2 now is the liquid phase, or as I cleverly call it, the non-solid phase. So this is going to give us H2. And as I said, this is going to be MC delta T. Now, for that to take place, we have to use, again, the mass, which if I had gone ahead and calculated this part right there, that's 0.0450 kilograms using 3 significant figures. So the mass is 0.0450 kilograms times the heat capacity of liquid water, which I gave you as 4,186 joules per degree Celsius. And then we take that times the change in temperature. Now when we say change in temperature, it's always the final temperature minus the initial or beginning temperature. That's generally how deltas work. And this is the Greek letter for D. Delta means difference. It's the difference or the change of the temperature. And in this case, it started off at 0 and ended up at 25. So it's 25 minus 0 degrees Celsius. And so when we put this into our calculators, we find that this value here is, I put the wrong number there. This is 4,710. And that indeed was the wrong value. That value right there was actually 15,000 joules. Yikes, went down my page too quickly there. So, now the total heat is equal to H1 plus H2, which is 15,000 joules plus 4710 joules, and round that off to 3 sig figs, we'll get 19,700 joules of heat. So, or if you want to put that in scientific notation, which I generally like to do, I don't like dealing with the commas. They're so messy and so many zeros. 1.97 times 10 to the 4th joules. Okay? So, that's how we do a 2-part phase change. The change of the substance from one phase to another, and then the amount of heat it takes to raise the temperature or lower that temperature for the next step if it goes down.